All right, good afternoon, everyone. Nice to see you. Small little group, that's good. I'm ready to answer any questions you might have on anything you like. So fire away. Megan.
I was wondering if we could walk through number 23 on the practice test.
Yep.
I was getting a little lost.
All right. So you have this problem where you're trying to find. Sorry. Get a couple things together here. This is the problem you want, right?
Yeah.
Megan, yeah. Okay, so you want to find E cell under these non-standard conditions, right? So, and they give you E naught cell, which saves you a little bit of work, right? So E cell, right, is going to be equal to E naught cell. Let me try that again. E cell is equal to E naught cell, right? Minus 0.0592 over N times log of K. Oh no, that's not right. That's the wrong equation. 4.0592 log of Q. Right? So Q in this case, right, is going to be equal to what? The concentration of Ag plus cubed divided by the concentration of MnO4 minus times H plus to the fourth. And that's it for Q, right? And you're given those concentrations, right? So you can plug them in. So we got E naught is equal to E naught cell, 0.88 volts minus 0.0592 over N. And now we got to figure out what N is. And so you can either break it up into half reactions to do that, or you can kind of see that you have 3Ag going to 3Ag plus. That's your oxidation, right? So you know that N is going to have to be 3, right, from that.
So is it just based on we'd look at the oxidation?
You know what? Sometimes it's a little harder to tell. I mean, the way you can always tell is by breaking it up into half reactions. It's basically doing what you would do if you unbalanced it, right? Step before. But a lot of times you can tell pretty straightforwardly by saying, oh, okay, I can see that this is the oxidation, because in this case, it's going from a metal to the ion. So you can tell that it's 3, because it takes 3 moles of electrons to do that. Otherwise, you can also see that, let's see, how else could you do it? Yeah, you can do it that way, or you can break it up in half reactions. Either way would work. So the log of the concentration, I don't know if you were given the same concentrations as I was here, but that's going to be 0.0100 the quantity cubed, right, divided by the concentration of MnO4, 1.90 times the concentration of H plus raised to the 4th power, right? So you just got to enter all that in, and that should give you your answer. So in this case, that comes out to be 1.01 volts. Does that make sense?
Yeah, thank you. The part I was stuck on was like finding the number of moles.
The moles of electrons.
Yeah. makes sense.
So the other way you could do that is you could say, all right, so my half reactions, my oxidation is 3Ag goes to 3Ag plus 3 electrons, right? And then the reduction would be MnO4 minus plus 4H plus goes to MnO2 plus 2H2O, right? So that's the oxidation. That's the reduction. And in terms of balancing this reduction, right, you notice that you need 3 electrons on that side, right? Because you have -1 and 3 plus. So 3 electrons makes it 0 on that side because it's 0 on that side. So there, so either for the oxidation or reduction, you should be able to figure out the number of moles of electrons. Good. Other questions?
Can we go over number 22 on the first pretest?
Number 22 on what?
On the first pretest?
Yeah. You mean from like the pretest one that I posted?
Yeah.
Yeah. Sorry, what number did you say again?
Number 22.
Yeah, good. So you have that reaction, and then you have these initial rate data, right? So what you want to do is see how the initial rate changes when you change the concentration of A and B, right? And so if you look here, the initial concentration of A was 0.05, the initial concentration of B was 0.05, and this was the initial rate. And then you go to the second experiment, and what changed? We doubled the concentration of A, right? Concentration of B remained constant, and the rate doubled, right? So the rate law, right, is going to be equal to K, A to the something, and B to the something, right? From these two experiments, we can tell that the dependence of A is first order, right? Because first order reaction, if you double the concentration, you double the rate. If it was zero order, then you double the concentration, there would be no change in the rate. If it was second order, you would double the concentration and the rate would quadruple, right? So in this case, you double the concentration, double the rate, that tells you it's first order in A. Now, what about B? Now you go here and you see that you only have one more data set to determine what the order is with respect to B. But unfortunately, the concentration of A is not held constant between this experiment and that experiment, right? But you already know the concentration dependence of A because you got it from this first set of experiments, right? So you already know that when you take A from 0.05 to 0.20, you've quadrupled A, so that's going to quadruple the rate. So you already expect a 4 times increase in the rate due to that. And now you're trying to figure out, okay, what was the additional effect due to doubling the concentration of B? Does that make sense? So notice what happened. You quadrupled A, you doubled B, and you quadrupled the rate, right? It went from 0.035 to 0.140, which is 4 times bigger.
So you look at the first value and the third value in the table?
You could look at these two. That's another possibility too. You can take any one. I mean, we could do it that way too. So you can look at this, the change from here to here. Here you double A, right? What do you expect from doubling A? You expect the rate to double because you already know it's first order with respect to A. you double B, and notice that there's no additional effect due to doubling B, right? So what does that tell you about the order with respect to B? Right? Was there any, see, you double, and going from the second experiment to the third experiment, you doubled A and you doubled the rate. You also doubled B. You already know that A is first order, so you already expect a doubling. So the fact that this didn't change any more than what you expected from A, even though you doubled B, tells you that the rate with respect to B is zero order. In other words, the two changes compound, they multiply together, right? Does that make sense?
When I looked at the explanation for it, they have like a ratio or something.
Yeah, I know. That just makes it more complicated than it needs to be, if you ask me.
Oh, okay.
I think it's just easier to look at the data and think about it, right? Because so in other words, if you had, let's say you had, let's just say, let me give you another set of data so you can see how this would work. Let's say you had A, B, and rate, right? And let's say you have, so you know, and let's say you already know that the rate is first order with respect to A, right? You already know that. So here you're going from 0.10 to 0.20 if you compare experiments 2 and 3. B is going from 0.05 to 0.10, all right? Now, let's suppose that this reaction, let's forget this problem for a minute. Let's suppose it was first order with respect to A and first order with respect to B, right? What would be the effect of doubling A? And let's say the rate here was 1, just to keep the numbers simple, okay? You double A, you'd expect a factor, you'd expect the rate to go up by a factor of 2. So you'd expect the rate to go to 2 just based on that. And if it was also first order with respect to B, right, this would go from 0.05 to 0.10. So you expect another factor of 2, right? So you would expect a factor of 4, right? Because you got to multiply the effects together. Does that make sense?
Yeah, I think so.
Right? Okay, so now let's suppose that you double B, and let's suppose this is the same data, but now when you looked at the rate, instead of being 4, it was 2, right? And now you didn't know B. You only knew that A was first order, right? So the effect of A was to double the rate. The effect of A, you know, is going to be to double the rate. What's the additional effect of B? Nothing, right? There is no change due to changing the concentration of B. Therefore, you know it's zero order in B. Let's take one more case. Let's suppose that this rate here, again, you know it's first order in A, and let's suppose you measure the rate after this experiment, you find that it's 8. Well, you expected a doubling, you'd expect it to go to 2 due to the A changing. So what was the additional effect from B doubling? Well, it went up by a factor of 4. So in that case, you would conclude that the order with respect to B is 2. But in this problem, the one that you were given, you already figured out from the first experiment there was first order in A. And then from the second set of experiments, you can figure out that it's zero order in B. Does that make sense? Good.
That makes so much more sense than their little write-up comparison thing.
Yeah, I think this just is more confusing.
Yeah.
I think it's easier to just think about it like that. Good. What other questions do you have for me?
I was also wondering about number 23 on the same one.
shoot, I just did that. Okay, so here they tell you the reaction is measured at several different reaction concentrations, okay? And now they're asking for the rate constant. So you have to know the rate law, right? Rate is equal to K times A times B to some integer, right? Some number. So in this case, they're asking for K, all right? In order to get K, as long as you know the rate at two different concentrations, and as long as you know the order of those two different reactants, you can solve this equation for K, right? If you know this, and you know this, and you know this, and you know M and N, right? So here in the data table, you have instances of all three of these: rate, concentration, concentration, right? But in order to use that, you still need to get the orders of the reaction, but you can get the orders of the reaction from how things change. So we do the same analysis we did before. Here, notice B stays constant, A doubles, and what happens to the rate?
Doubles.
Doubles, right? So what do you know about M? What's the order with respect to A?
The first order.
Yep, correct. And then for B, now in this case, let's see, what do we got? Can we look at, so we have to do the same thing again, right? Because if you look at this data, right, here we doubled A and we doubled B, but you already know that doubling A should double this, right? So doubling A would result in an order of 0.18, right? 0.09 times 2, right? That's 0.18. So, but what did you get instead? You got 0.72. So that's 0.18. Let's see. So 0.72 divided by 0.18 equals. So the effect of doubling B in this case was to increase the rate by an additional factor of 4. Right? Because again, you'd expect from here to here, you'd expect this. So in other words, one way to think about this, you can kind of say, oh, okay, doubling this should increase it to 0.18. How much did it increase in addition, right? So you go, oh, 0.18 to 0.72, I doubled this, 0.18 to 0.72 is a factor of 4. So what does that tell you about the order with respect to B?
Is it second order?
Yeah, exactly right. Second order. Very good. Right? Because that was the additional factor that you see, yeah? And then, okay, so now you know the orders. Now you can take any one of these data and plug it into here and solve for K, right? So K is going to be equal to A raised to the 1 power, B raised to the 2 power. Oh, sorry, no, that's wrong. K is going to be equal to the rate divided by A raised to the 1 power, B raised to the 2 power, right? So just take any of these and plug it in. 0.045. We could take the first one across. Just make sure you take the same row, right? Divided by 0.09, divided by 0.09 squared, right? And that should give you 62. Does that make sense?
Yeah.
Perfect. Good. Yeah, that's kind of tricky when they don't hold one of them constant. And they're both changing, it makes it a little more difficult, right? Because you have to take into account that change that you know is going to happen and then figure out, okay, what's the additional change due to the constant change in the concentration of B? Okay, other questions?
Just one more on that one. Could we also do 25?
25, sure. All right. So here, you have to know those. You have to know those integrated rate laws. So let me put them up here for a minute just to have a look at them. A really good table in the book.
No, I actually think I asked for the wrong one.
Oh, is
Oops,
that the wrong one?
I think I meant 31 actually.
Okay, no problem. This is a good problem though to know. Let's just look at this one since we have it up. The decomposition of bromine is a function of time. Two different plots of the data are shown here, right? And you're asked to find the order and rate constant for the reaction, right? So first of all, the fact that you plot the log of bromine versus time and you got a straight line tells you what? Tells you what about the order?
It's first order.
It's first order, right? And so I'm just trying to see if I have a good place to, yeah. So this table, actually, this is a little easier one for me to display here. This table right here, the integrated rate laws, right, for the different orders. It's a good table to, keep handy, right? Because that tells you, aha, if I plot log of A versus time and I get a straight line, that's first order, right? And then they also ask for the rate constant, determine the rate constant. The rate constant you can get from the slope, right? So here you have a linear line. You can figure out the slope of that, right? And the slope is going to be equal to minus the rate constant, right? So once you figure out the slope, and you just do that by the change in y over the change in x, and then take negative of that, and that'll give you the rate constant. So that's how you do that problem. But that's not the one Francesca was asking about. You were
What
asking,
page number was that?
pardon me?
What page number was that you had on in the book?
Oh
in the
yeah,
text?
that was page 670.
Thank you.
Yeah. Okay, so it was 31 you said, Francesca?
Yep.
All right, so this is a mechanism problem, right? So what you want to do here is you want to remember that the order is always determined by the slow step, right? But if there's any intermediates in the slow step, you got to get rid of those intermediates, right? Those are the two basic ideas behind this problem right here, okay? So let's start with the slow step. And we could say that from the slow step, we know that the rate is equal to K, let's call it K2, even though it doesn't have a K2 there, for that step, times the concentration of H2 times the concentration of N2O2, right? So now, if this expression does not have an intermediate in it, then we'd be done, right? And that would be the rate law. But because it has an intermediate, right? And how do you know this is an intermediate? This N2O2 does not show up in this balanced equation, right? So that's how you know that's an intermediate. So the question is, how do you get rid of intermediates? You got to try to express their concentration in terms of the concentrations of other reactants or products, okay? And you can do that from this first step because of this equilibrium sign that's there, all right? Because when you have an equilibrium, what does that mean? That means that the rate of the forward reaction is equal to the rate of the reverse reaction, right? So based on the same reasoning then, the rate of the forward reaction right, is equal to concentration of H2, concentration of NO squared NO squared, right? That's the rate of the forward reaction times K1 is equal to the rate of the reverse reaction, which is equal to K minus 1 times N2O2. All right. So this is the part that's a little tricky, right? You got to basically take this first step here that's fast and say, aha, these rates are equal. So what's the rate of the forward reaction? Well, it's NO squared times its rate constant, right? And the rate of the reverse reaction is its rate constant times the concentration of N2O2. And then you go, aha, now I can solve for the concentration of N2O2. N2O2 concentration is equal to K1 over K minus 1 times NO squared. Right? Then I could take that and plug it into there. Right? And if I do that, I get the rate is equal to K2 times H2 times K1 times K to the minus 1 times NO, the quantity squared. And then all these K's can basically be lumped into one K. So you get K H2 concentration times NO squared concentration. So that's the rate law that's predicted by that mechanism. It's been a while since we did that, hasn't it? Okay, so, Sophia, do you have a question?
Yeah, and it's a simple question, I think, but I was just looking at the table of electrode potentials for the half reactions. And I understand that every time that we look at the bottom reaction, like if you look at one, it will react with any reverse reaction that's in the bottom.
Yeah.
How do we know, like, because I was just thinking we can choose any of them and then make that one the top one and then the other one the bottom one.
No, because you can't.
That's assigned?
You can't change the order in the table.
No, I know, but
Because the order in the
You could-
table is based on the potential energy of the electron, right? So you can't change that part.
But like if I say, for example, hydrogen with, I don't know, copper. If you say copper will react with hydrogen, then that
Let
copper is on.
me pull the table up real quick, okay? Hang on for 1 second.
Okay.
Okay, so what we're saying is that any reaction on this table is spontaneous when paired with the reverse of a reaction below it. So for example, let's say let's say you have so 2H plus 2 electrons goes to H2, and we're saying that that's spontaneous when paired with any reaction below it. So let's say CD, let's use this one, CD goes to CD2 plus 2 electrons, right? And what we're saying is that when you pair these two together, right, to get this overall reaction, that will be spontaneous, right? Because notice this is the oxidation, this is the oxidation, this is the reduction, right? Oxidation occurs at the anode, reduction occurs at the cathode, and E0 is equal to E cathode minus E anode, right? Which is equal to 0 minus E anode, which would be minus 0.40.
So it's
Then becomes
0.40.
plus 0.40 volts. right? So that's why any reaction in the forward direction is spontaneous when paired with the reverse of a reaction below it. But it has to be below it, because look, if you try to pair it with a reaction above it, let's try to pair it, let's say, with the copper one. Okay, so then we got the same thing, 2H plus 2 electrons, right, goes to H2. And then we got copper, right, going to copper 2 plus 2 electrons. So looks very similar so far. 2H plus copper solid goes to copper 2 plus H2, right? But now when we notice that this is the oxidation, which occurs at the anode. This is the reduction, which occurs at the cathode, right? And E0 for that is E cathode minus E anode, which is equal to 0 minus the copper reaction, which is 0.34 volts, which is equal to negative 0.34 volts, right?
Okay.
So that one is not spontaneous. Why? Because I try to pair a reaction with the reverse of one above it. And that's never spontaneous. Only when you pair with the reverse of one below it will it be spontaneous.
Okay, that makes sense. I guess I was just thinking we could interchange which one we see as above, you know what I mean? But now it makes sense that the voltage would be negative if you do that. Like you can't change the anode and cathode. Okay.
Right.
That makes sense.
Yeah.
Thank you.
Good. You're welcome. All right. What else? What other questions do you have for me?
I had a question on 24 for the exam pre-exam.
Yeah. Let's see. For the exam 3, you said, right, Sophia?
Yes.
Sorry, one more time. What number did you say?
24.
24?
Yes. Sorry.
Oh, great. This is a great kind of question. So you know that for this electrochemical cell, is this the right? This is the right problem, yeah, Sophia? Yeah. You know that Q is equal to 0.010 and K is equal to 855. So what can you conclude about E cell and E naught cell? So first of all, let's forget about electrochemistry for a minute and go back to our equilibrium chapter. What do you know about a reaction if Q is less than K? If Q is less than K, what can you conclude about the direction that the reaction goes right? Reaction goes to the right? So if a reaction is spontaneous in the forward direction under whatever conditions you're at, what can you conclude about E cell?
It's positive.
Correct. Therefore, E cell is greater than 0, right? So we know that. Now, that's how in order to get that, you compare K and Q. Now let's just look just at K for a minute. K is 855, right? So remember, so there's two ways to think about this. One way is conceptually and one is using the equation. Let's think about it conceptually first, and then I'll show you how to think about it with respect to the equation, all right? K is equal to 55. What does that mean? That means if remember what E cell tells you. E cell tells you the spontaneous direction when Q is equal to 1, right? So when Q equals 1, which is, you write the standard conditions, the fact that K is 855 tells you which direction is this reaction going when Q is equal to 1. Is it going to the right or to the left?
To the right.
To the right. When Q is equal to 1, reaction goes right. So if the reaction is spontaneous under standard conditions, what does that tell you about E naught cell?
It's positive as well.
Correct. Therefore, E naught cell is greater than 0 as well. Okay. The other way to think about this is with the equation E naught cell, right, is equal to 0.0592 over n times the log of K, right? If K is some number greater than 1, oops, I forgot the negative sign here, right?
Yeah. Yeah, there's a negative. No, I don't think there's a negative there.
Oh yeah, no, there's no negative. Sorry, it's the delta G one that has a negative. If K is greater than 1, which it is in this case, then the log of K is positive. And what does that tell you about E naught cell?
Positive.
It's also positive.
Sorry. Yes. Can you hear me?
Does that make sense? So
Yeah,
that's
and if it's
another way
less
to
than
make-
1, it's negative.
Pardon me?
If it's less than 1, it's negative.
Correct. Yep. K is less than 1, it's negative, because what does that tell you? If K is less than 1, that means that when Q is equal to 1, this thing's going to the left, right? Which means it's non-spontaneous, which means that E naught cell is negative.
And so my question is, that's going to change depending on the values of Q and K you give us, because it's not always that both E cell naught and E cell are going to be both
Right, so
positive
let me
or
give you-
both
give you
negative.
Another example. Let me give you another example. Let's suppose, what if, let's say Q is equal to 2000 and K is equal to 855. Then what can you conclude about E cell and E naught cell?
E naught cell is positive.
Correct, because we haven't changed K. Very good. What about E cell?
Negative.
Correct. Right? Because
Because
you
Q is
know,
less-
just again,
Q is
go back to
bigger than K.
equilibrium, right? If Q is greater than K, which direction is this reaction going?
To the left.
To the left. So what does that tell you about E cell under these conditions?
It's negative.
Negative. Yeah.
Okay, that makes sense.
Um,
Okay, so there is cases when.
Standard cell is 298K, that's true. But the more important thing about standard conditions is that it's at 1 molar or 1 atmosphere, right? So when we say standard conditions, we always mean Q is equal to 1, right? Because for any equilibrium, if the concentrations are 1 molar and the partial pressures are 1, then when you figure out Q, it's going to be equal to 1. So standard conditions are Q equal 1. That's the important part of it. The most important part of it. Taylor.
It might be easier. Oh, I got a screenshot of it. But it was basically on the number of electrons that transfer.
Uh-huh.
And there it is. Okay, so I can tell you where it is in the book. It's not on the problem sets.
Okay.
But basically it's manganese O4. Wait, well actually
You have a page number?
I do. It's hold on, what page was this? This was oh God. It's the chapter 20 review, number 9.
Okay. Chapter 20,
Chapter 20 review number 9. I think that's page,
review. Are you talking about the self-assessment quiz?
yeah, the self-assessment quiz. That's it.
Yeah,
Yeah, 900 and,
I have it here.
okay, cool.
You're thinking of that one. Is that the right one?
Let me see here. I
Can you read that?
think I can. Yes, I can. I can read that. Yes. Yes, it's that one.
Okay.
Yes, it is that
So you
one.
want to find E cell, right? For that reaction, and you're trying to figure out the number of electrons that were transferred.
Yeah, I got the right answer. I was off at first, but I kind of guessed it. But I messed up the electrons transferred. I said it was 4 instead of 3, I think. Yeah.
Right, right. So this is the one we were looking at a little bit earlier. Maybe you weren't on yet, but
Yeah.
one way to do it is to say, okay, you can just look at silver goes from there are 3 silver atoms that go from 0 to +3. So you know
Okay.
there must be 3 electrons.
Mm-hmm.
So N is equal to 3. The other way you can do it is you can also break it up into the half reactions and see that for MnO4 minus, 4H plus, right? You have to, in order to balance that half reaction, you need 3 electrons.
Okay.
But the easiest way to do it, if you have a metal like that, it's really nice, because if you have a metal, right, you can just tell from the metal that if it goes from 0 to +1, and there are 3 of them, right, then there must be 3 electrons transferred.
Okay, so if you can make the same case for the metal, why can you not make the same case for the hydrogen? Like the 4
Because the
hydrogens.
hydrogen is going to H2O, so oxygen is involved there. So you have to account for the
Ah.
oxygen,
Yes. Okay.
right?
Okay. So
But
you
like,
basically
let's look
focus
at
on
another
metal
problem
there.
here, and just while we're here.
Okay.
How many electrons are transferred in this one?
Is that PB2 plus?
Yep.
Okay. Yeah. So then 2 would be
2,
transferred.
right. And since only one PB going to one PB2 plus, then you know that the N is equal to 2. So that's the shortcut way to do it. The long cut way to do it is to just figure out what's oxidized, figure out what's reduced, and break it up into the half reactions and see how many electrons you need to balance each half reaction. But most of the time you can do it this shortcut way.
Okay.
There's another one up here. How many here? Well, it's not balanced. Sorry, that's not a good one. You know, I think all of them that are on this page, you can probably do this way. Let's see, what about, well, those are all pretty easy.
Yeah.
Yeah.
I think I get the concept now, though. I think I was focusing on the wrong one. I was focusing on the hydrogen, and I was like, "Oh, that makes sense," you know. But then,
Yeah.
oxygen.
Yeah. If it wasn't going to water, then you could use hydrogen. But since it's going to water, you can't,
Okay.
because
that makes-
water has a charge. The oxygen has a charge too, right?
Okay. Okay, that makes sense. Okay, cool. Yeah. And then sorry, I just have one more. It's really quick. It's on the chapter 21 review or self-assessment quiz. It is number, let me get the self-assessment. It was number, I think it's 6. It has the rate. It gives you the rate PB 206, and then it's like the rock.
Is it this one? This is 6?
Yes. Or wait. No, I think it's down for the number 8. Number 8.
Oh yeah, number 8. So remember, we didn't do lead 206, uranium 238, and that will not be on the exam.
Oh, okay. All right, so I can stop there.
It's a little more complicated to figure that out.
Okay.
I can show you how later if you want to stick around, but it's a little more complicated because these things, the mass ratio has to be converted into a mole ratio, because what matters are the moles, not the mass. All right.
Okay. I
So
kind of thought
in
about
terms
that.
of this kind of problem, you would be responsible for understanding something like question 6 or question 7, but not question 8.
Okay. 6 and 7, I understand. I was like kind of confused with 8 because
Yeah.
that makes sense. We didn't go over it.
Yeah, we didn't really cover it.
Okay. Okay, cool. All right. I'll
It's
just,
just, it's not that much more complicated, but it's just a little bit more complicated. You got to convert from grams to moles for both of them and then get the mole ratio.
okay. It's the same concept though, right?
It's the same concept. Yeah.
Okay. That's okay. Because I kind of thought about that because when it said it was wrong, I was like, you used like the mass ratio or like the number it gives you, and you have to convert that into moles. That makes
Right. So there are some things in the chapter that we didn't cover, and that was one of them, the uranium. We mentioned it in terms of how old the Earth was, but we didn't really go into the details of how that gets calculated.
okay. Okay. All right. And that was it. Thank you.
Yeah, no problem.
I'm sure, sorry, what time will the final be available on Monday?
10 a.m.
Until 12 p.m.
Both exams will be available from 10 a.m. to midnight. The exam number 3 will be on Thursday from 10 a.m. to midnight, and and the time is 70 minutes. The final is on Monday from 10 a.m. to midnight, and the time is 110 minutes. The final has more questions, that's why.
How many questions are on the final?
50.
Thank you.
Yeah.
For the problem that you were just doing, and you were explaining that there was 3 moles of electrons transferred. What were we trying to find using those moles?
So you were trying to find E cell.
Mhm.
So you have to use this equation. And a lot of these electrochemical equations have this N in them, right?
Mhm.
Where N is the number of moles of electrons transferred in the reaction.
Mhm.
So that's where we were trying to get N for this for the overall reaction, these are the 2 half reactions.
Mhm. Okay, and I have another question.
Yeah.
Where does the log come in? Because I saw in the book it says ln and then it says log.
Right. So the final equation in that case is log.
Mhm.
Right. So the where it says ln, what page are you on there in the book, Marlon?
918.
918. So what happens there? Let me see. I have to. So what's going on here is that I'm just going through and deriving this equation. Okay, I'm showing where it comes from because this equation comes from the delta G equation. And so it's kind of weird. Physical chemists tend to like to use the natural log of Q, but electrochemists tend to like the base 10 log of Q, base 10 log. So from here to here, all I did was I combined all those constants and converted the natural log to base 10 log. And that's how you get this equation. But this is the equation you want to use for the E cell. This is the equation you want to use for delta G. So you got to remember that this one has the natural log. This one has the base 10 log.
Mhm. And then there's one with K. That's standard.
Correct. And that also has the base 10 log. It's this one. Where is it? Here. is right, where is it? Yeah, this is a good place to see that all these relationships together, right? It's not really showing up super well, is it? This is on page 917, right? And this has the three relationships, because once you know one of these, you know all three because they're all related, right? Delta G naught, E naught, and K are all interrelated. And they're related by these three equations. So this is the one I think this is the one you're talking about with K.
Mm-hmm. Yeah. And then ln of k. There's also ln of k. So I don't know. I get confused between log and ln.
Yeah, I know. You got to be careful. So basically, the thermodynamics chapter that we did, right? Which was chapter 19. It's all natural log over there for thermodynamics. For electrochemistry, it's all base 10 log. And it's just historically been that way. And so that's the way we just have kept it. You could express these reactions, these equations with either one, but for historical reasons and by convention, this is the way those reactions, those equations are expressed. It's just the way it is. So you just got to keep it straight in your mind. Just, write these equations down on your cheat sheet so that you have them all handy. And then just make sure you write ln or log, depending on which one it is. And then be careful on your calculator too, to make sure you hit the right function.
Mm-hmm. Okay. Thank you.
Yep, you're welcome. What other questions can I help you guys with?
Can we go over balancing a redox reaction in basic solution?
Sure. Yeah, let me just let me get a problem here. I think the easiest way to do it is just to work an example problem. So let's see. Let's do Cl minus plus MnO4 minus goes to Cl2.
You have to bring the page down, true.
Oh yeah, you're right. I gotta fix my things.
Thank
I moved it around. Hang on. Cl minus plus MnO4 minus goes to Cl2 plus MnO2. So that's gas, solid, aqueous, and aqueous. But I won't keep writing those things over and over just because it gets annoying. So, so you start like you always start by assigning oxidation states, right? So you got Cl is -1, oxygen is -2. There's 4 of them for -8. So manganese is going to have to be +7. And then Cl2 is a pure element, so it's 0. On this side, you have -2 for the oxygen, so you have +4 for the manganese, right? So here's my oxidation, right? And here's my reduction. So I write down the half reactions, oxidation, Cl minus goes to Cl2. And I write down my reduction. MnO4 minus goes to MnO2. So far, so good?
Yeah.
Okay. Then first thing I got to do is I balance with respect to mass, right? So I got 2 chlorines on this side. So I have 2 chlorines on that side. Okay. And then on the bottom one, I have manganese on this side and manganese on that side, right? So all the things other than oxygen and hydrogen are now balanced with respect to mass, right? Next thing is I balance oxygen, right? By adding what? Water, okay? So there's no oxygen up here, so I don't have to worry about that. Here, I have 4 oxygens, 2 oxygens, so I got to add 2 waters to that side. Let me zoom out a bit here. Oops, too far. Okay, then the next step is to balance hydrogen by adding H+. So I have 4 hydrogens on that side, so I got to add 4 H+ over there, right? So if this were acidic, I'd go on to the next step at this point, which would be balancing electrons. But because it's basic, right? So this is in basic solution, I got to get rid of the H+. And how do I do that? By adding OH minus, all right? But since everything is already nicely balanced, any OH minus I add to one side, I got to add to the other side as well. All right, so there's no H+ in this oxidation reaction, but there is in the reduction, right? So I want to add plus 4 OH minus to neutralize those 4 H+, but then of course I got to add plus 4 OH minus to that side. All right, so my reduction reaction becomes MnO4 minus plus 4 H2O, right? Because those combine to form H2O, goes to MnO2 plus 2 H2O plus 4 OH minus. Does that make sense so far? Reed, does that make sense?
Yeah.
Okay. So now I've neutralized the H+. The next step is to balance the charge. I'm going to go ahead and bring the oxidation reaction down here so that they're close together again. 2 Cl minus goes to Cl2. And then remember, you balance, sorry, this is Cl. Then you got to balance the electrons, right? You got to balance the charge by adding electrons, right? So you got 2 minus on this side, so I need 2 electrons on that side, right? Down here I have minus 1 on that side, 4 minus on that side, right? So in order to get this to balance, I'm going to need 3 electrons over here, right? Because now I have 4 minus on both sides. Does that make sense? And then my last step is to add the half reactions together. Sorry, not yet. Sorry, I forgot. You got to multiply, you got to equalize the number of electrons first. So I'm going to multiply this by 3, and I'm going to multiply this by 2. And I'm going to do one other thing before I proceed. And you could do this at any point, but I notice now that I have 4 waters here and 2 waters there, right? So I can cancel these and make this a 2. Right? Because there's just the same thing on both sides. You can cancel it out. Okay. So then when I multiply all this out, I'm going to get from my oxidation, I'm going to get 6 Cl minus goes to 3 Cl2 plus 6 electrons. For my reduction, I'm going to get 2 MnO4 minus plus 4 H2O plus 6 electrons goes to 2 MnO2 plus 8 OH minus. Okay, and then notice what happens here. My 6 electrons cancel, right? So when I add these together, I get 6 Cl minus plus 2 MnO4 minus plus 4 H2O goes to 3 Cl2 plus 2 MnO2 plus 8 OH minus. Okay, so then you should always check these, right? So let's check masses first. 6 chlorines, 2 times 3 is 6 chlorine, so that's good. 2 manganese, that's good. 2 times 4 is 8, plus 4 oxygens is 12. On this side, I have 2 times 4 is 8, plus 8 is 12, right? And then hydrogens, I have 8 on this side, and I have 8 on that side. So we're all balanced with respect to mass. We should also check charge. I got 6 minus and 2 minus is 8 minus on that side. And I have 8 minus on that side. So it all checks out. It's all balanced. Does that make sense?
Yeah, that helped a lot.
Great. What else are you struggling with? Okay, I think I'm gonna stop the recording. I'll still stick around and answer more questions, but I think that's probably enough for the recording. So I'm gonna stop the recording here, but I'll still stick around and answer more questions. Thanks.